Any questions about last class? Okay, so currently I am, and you can ask me questions later if they come to mind. I'm sharing the screen from the class webpage. I wanted to highlight a couple of things. One is that the second homework is now up online. If you click on it, you will see the PDF. The PDF has the link for where you can submit the answers, just like last time. You go to a form and you can upload it. It has five questions. The second one is very similar to what we did last time, deriving the variance in energy, but now it's the third moment. So it's going to be a bit more algebra, but hopefully you will learn through it. The others are all not too hard, but and especially after today's class, when we work through a model problem, they should seem easier. If you tried them before today's class, they might be a bit harder. And it's due in exactly a week from now. The first homework is graded. I'm going to release it through Slack today. What it means is that I will send it to you as direct messages at the end of the class. I want to do it in a realistic manner as I would have done it in a classroom. So you see only your grades, not anyone else's grade. And a couple of you are not present in the class today. So if you're watching the video later, you should have the answer in your Slack direct. You should have the graded thing in the Slack direct message. Most of you did well, except, well, all of you did well. One of the problems, so it was just, I'm not going to release the answer key for this first homework. I will release the answer key for all homework starting on homework 2. The first one was just background material. The one problem where many of you tried to cut corners or were a bit sloppy, and so that's why you will see that you have received 98 on 100 or something like that, is this problem number 4, in which you had to derive the heat capacity for the Einstein model and the Debye model. And in the low temperature limit, many of you just said it goes to 0. But the question wanted you to find the expression as per which it goes to 0. That happens to be T cube for Debye and exponential in temperature for Einstein. So when you see your solutions, look at this carefully and think what you did wrong. Some of you did get it. And this is something we will be revisiting later. So yeah. And apart from that, people did well. And some of you, if you have scored below 90 in this homework, then you should be careful. That's how I would say. If you have scored above 90, you are probably fine. If you have scored below 90, think hard because the homeworks are going to get tougher. Okay, great. So let's go to today's class. That's those the 2 things I already mentioned. Homework 2 is out. Homework 1 you will be given soon. And the third point I want to mention before I start with today's material is I have provided PDF of a nice paper, of a very nice paper by Roy Zia and Joe Reddish. Joe Reddish was or is a professor in physics at UMD. This paper concerns the Legendre transform and the idea of natural variables, which is something we have already mentioned many, many times in the class and to keep coming up again and again. I really recommend reading this paper. It will hopefully give you more intuition on top of Chandler chapter 1, thermodynamics, and Callan's book, which you did in 684. This paper will give you some intuition into what we are doing. Okay, so let's go to today's material. So today we are going to be looking at a simple problem and try to solve it using microcanonical ensemble and using canonical ensemble, and just develop intuition for how all of this machinery that we have been developing so far, how can it be put to use. So just to recall so far, what have we done? The thing we have really talked about is that entropy can be written as a function of number, volume, and energy. These are the natural variables for entropy in thermodynamics. The equivalent of this in the microcanonical ensemble, when you have an isolated system, is the number of states, which is also a function of MVE. And this entropy is related to this density through KB ln omega. Similarly, we looked at A of NVT And there we had a minus sign, and that came from minus kb ln z of nvt. This was the canonical partition function. Did I write z or q? I think I wrote q, right? Yeah, this changes book to book, but the most important thing is I have defined the variable of which it is a function of. That's the most important thing. So it doesn't matter whether you call it q or z, or you want to use a Greek letter for it. What did we, yeah, we used q last time, so q and vt, and that gives us a. Okay, great. So these are the 2 points we have. And again, then we showed that they don't really carry new different information from each other. It's a question of how you set up the problem. In the thermodynamic limit, they carry the same information. How did we show this? We showed that q of nvt is Laplace transform of omega nve. And anytime you have as n tends to infinity in the thermodynamic limit, anytime you have a Laplace transform or a Fourier transform, you're changing your basis. Instead of looking at time, you're looking at frequency or things like that. You're not really creating new information. It's the same thing. So they are really they carry the same information. It's a question of how do you set up the problem. So in order to get more intuition for this and also help you work with the problems in homework 2, let's look at an illustrative example. So illustrative example to see this in action. So I'm going to set up a problem. Pay attention, because I'm going to ask you, what do you expect the answer to be? Before I go and use microcanonical and canonical and everything to derive it, I want you to think about what the answer will be. So the problem is as follows. We have n particles, capital N, which are distinguishable. So you could imagine it could be you all, for example, who are distinguishable from each other. None of you are twins, as far as I know. They are independent, which is also fairly true. You act independent of each other, although in a classroom, you probably influence each other's behavior. But here we are going to assume that you are independent. And interestingly, here we say that any particle can be in one of 2 states with energy either 0 or epsilon. Okay. So this might seem like, oh, what's a strange example, but this is actually a very nice way of setting up problems in StatMech. And this is where StatMech starts to show its beauty. You can take a complicated problem and set it up in a nice way, and then you can use your tools, whatever you have already done in the last 4 lectures, and derive all sorts of wonderful properties. So how does it look like? So the way we can draw it visually. So you can imagine that you have states like this, where you have a high energy state where energy is equal to epsilon, and a low energy state where energy is equal to 0. And any particle can exist either in this state or in this state. You can have something that looks like this. Okay, so any given particle, this is particle number 1, particle number 2, particle number 3, dot, 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 particle number n. They can exist in state number, the ground state or the excited state. So my question for you is, at 0 temperature, now forget about statistical mechanics, just think common sense. At 0 temperature, what should be the average energy of the system? And similarly, what should be the average energy of the system at infinite temperature? When I say system, I mean all n particles. So here, this was per particle. Okay, so let's call it E1, just to be careful. I will be using capital E without any subscript. I will be using for the full system. E1 means 1 particle. So any ideas? What should this be without doing any math?
So, can you hear me?
Yes, absolutely.
So, I think at 0 temperature, the average will be 0 because
Uh-huh.
all the particles will be at the level 0. For infinite temperature, uh, I think it will be epsilon by 2, like half of them will be in 0, half of them will be in epsilon.
Almost correct. Thanks, Kishle. Does anyone think Kishle missed something in the second one? He missed an N, right? It's because we are talking about the extensive thing. So yeah, per particle, it should be epsilon by 2. So does this make intuitive sense to everyone? This is all we are saying is that at zero temperature, there is a ground state. If you have done quantum mechanics, you probably think that the ground state is unique. And so at zero temperature, everything falls into the ground state and the average and the total energy is zero. At infinite temperature, it doesn't matter. The entropy should dominate, right? That's the intuitive idea. At infinite temperature, you can be in up or down, excited state or ground state with equal probability. You can be in this one or you can be in this one, and it's the temperature, the fluctuations are so high you can fall anywhere. So this is the intuitive picture that you would have expected if you hadn't done any StatMech. Now let's see if our two tools so far, which is the microcanonical ensemble and the canonical ensemble, if they give us this result, do they agree with each other? Do they agree with our intuition? And this process will also give you some experience in how to set up a problem and how to solve it. So which one should we start with? Should we start with microcanonical or canonical? What do you all think? Do you have a preference here? No one has a preference? Let's start with microcanonical. Okay, so approach one. And you might think here, well, why do you say we can start with either approach? Maybe is the system coupled to a heat bath or not? If it is coupled to a heat bath, then we should do canonical. But as you will see, in a problem like this, you can actually start with either approach. It doesn't matter. It's really up to you. You just have to be careful in setting it up. So approach one, let's think about a micro canonical ensemble. And in order to set it up, what do we need to think about? We need to think about omega of n v. There is no volume in this problem, right? So the volume is not a variable that we are varying, so it disappears. We are going to think of omega as a function of n and e. If we can write down omega as a function of n and e, then we can get the entropy out of this by doing this. So that's our game plan. So let's write down, this is our game plan. This is our plan of attack. We are going to calculate omega of ne, from which we are going to get s. Once we have s, we can do beta is equal to 1 by kBt and use our definition of temperature from thermodynamics that we showed earlier. This becomes partial ln omega by partial E at constant n. We have our temperature. And from this, we are going to manipulate to get our internal energy. So because we will have the temperature as a function of energy, and we will be able to manipulate this expression to get our energy as a function of beta. And that's what we want to see. We want to have an expression which gives us these two limits. But the thing about these expressions is they don't tell you what happens in the intermediate temperature. And even though Kishle showed us that we can write this, if any of you have a shortcut way of telling me what will be the average energy at some intermediate temperature without doing StatMech, I'm very curious. You get extra bonus points for a homework of your choice. If you can do it without doing StatMech, I would be very, very curious. So let's do this. How should we proceed? So we have to calculate omega of ne. In order to calculate omega of ne, what does that mean? Omega of ne, and this is also why I like this example, because it gives you intuition into what this is. So omega of ne is the number of ways the system can have a total energy of E, right? So, okay. And I guess one more thing I should mention for this problem, which I forgot, that defining the microstate of this system microstate of this system can be uniquely defined by a set of numbers that go from n1 to n2, this is small n, up to n capital N, where each number is binary. It is either 0 or 1, 0 or 1, 0 or 1, depending on whether you are in the ground state or in the excited state. You could have also called it 0 or epsilon, 0 or epsilon, doesn't matter. So if you have nu is equal to 0, 1, 1, 0, 0, 0, 1, 1, then you know exactly the microstate this system is. If you have nu is equal to 1, 1, 0, 0, 0, 1, 1, you have to have n such binary numbers, and then you know exactly what is the microstate of the system. So that's how we define our microstate here. So the question is, how do we calculate omega? So in order to do that, let's first think about what let's say the example that I drew here, I have 1, 2, 3, 4, 5, 6, 7, 8 spins, right? So let's consider the example where n is equal to 8. I'm not talking about small n. I'm going to be interested only in the thermodynamic limit. Let's consider the example n is equal to 8. What is the energy of this microstate that I wrote down here? It is 1, 2, 3, 4, right? Because 4 of them are in epsilon state, so the energy is 4 epsilon. What would be omega for this possible configuration with n is equal to 8 and E is equal to 4 epsilon? How many microstates could we have created which have this energy? Any idea? Remember, we looked at some math concepts in the very first class. That's your hint.
C8-4.
So 8C4, right? Thanks, Jingchen. Why C? Why not P? Why not permutation? Why did you say combination?
Because the order of the particles doesn't matter in getting the total energy E.
Are you sure that's the answer? I would say the order actually matters. They are distinguishable, and that's why you have C. No, you're right. If the order mattered, then you would have permutation, correct? You're correct, absolutely. So order does not matter. It could be anywhere. So it's going to be 8C4. And that would be 8 factorial by 4 factorial, 4 factorial. Is this clear to everyone? Okay, I assume this. Yeah, go ahead. Kishla, is that clear?
Yeah, I just said yes.
Okay, good. So now let's try to generalize it. So now we are talking about omega of n comma E. And let's say that our E, we are thinking about in units of epsilon, right? That's our natural energy unit over here. There is nothing fancy about it. It could be KT, it could be Joule, it could be whatever you want. So in this term, we know that M is going to be more than equal to 0, less than equal to capital N, right? That's the total energy of the system. So in this case, we can just generalize and write down our omega of Ne by the same argument that we did over here, but now it will be n factorial divided by small m factorial divided by n minus m factorial, or n choose m. Okay. So we have our omega of Ne. In principle, the problem is solved. All we need to do is to go back to formula 1, use formula 2 in equation 2 in equation 1, solve for entropy as a log of this, and do our algebra. It's as a mathematician would call it, it's all trivial from here on. But mathematicians can be a bit, there is a joke. One point in my time, I tried to be a mathematician. So I used to like all sorts of mathematician jokes. And one of them was that two mathematicians are arguing over something on the blackboard. And they argue and argue and argue and argue. And then they go out. And finally, their conclusion is that it's trivial. Why is it trivial? Because it can be proved in 5 pages, and they see what the proof is. And they say that's trivial. So it is that kind of trivial. It's not done from here. You still have to do algebra. Let's work through it. But the key physical concept here is that omega n e is n choose m. Okay, great. The order does not matter in how you pick up the particles. They still contribute to the same energy, even though they are distinguishable. So let's go to, actually, let me check something before I go down a wormhole. This example is also done in Chandler's book, if it confuses you. So just to remind you, omega n e is the number of ways where E is equal to m epsilon, m objects can be chosen from n, and we have that. Okay, so now we have to calculate entropy. So S is equal to kb ln omega of ne. And this was our equation 1, and we know beta is going to be partial derivative of ln omega by partial E at constant n. Volume is not a variable in this problem, so we don't consider it. So let's write down our ln omega using equation number 2. So that will be ln n factorial minus ln n minus m factorial minus ln m factorial. Okay, so at this point, we would actually get stuck in a terrible way. You will have to make, so far, we haven't really done many approximations, but now we are going to make an approximation that n is much more than m, okay? Which itself is much more than 0. Or rather, let's say it's much more than 1. So we are dealing with large numbers. All the numbers are very large. And now we have to, let's call this one as equation 3. We need partial ln omega by partial m. So the good news is this one does not depend on m, but both of these do depend on m. So we have to differentiate it, right? So we need partial ln omega by partial m. In order to do that, let's use Stirling's formula first to simplify this ln omega. And ln omega will be ln n factorial. I'm not going to care about the first term because it has no m dependence. And minus n minus m ln n minus m minus m ln m, correct? So partial ln omega by partial m, do this carefully, is going to be partial by partial small m of minus n minus m. If I go too fast, then just let me know, okay? The most important thing is that you stay with me and don't fall asleep. Minus m ln m. And now we have to do the product rule to get both of them. So let's go to this first one. That's going to be, I'll just use red for that one. That's going to be minus n minus m, 1 by n minus m due to the wonderful properties of log, multiplied by minus 1 because we have a minus m over there. Now we go to this second one. That's, we did not do the second part of the first one because we kept the n minus m constant and we differentiated the log, but we also need to differentiate this first term itself. That will be again minus multiplied by ln of n minus m, and once again a minus 1, right? I have not written anything profound here. It's just doing bookkeeping algebra carefully. The second term will be minus m multiplied by 1 over m minus ln n. So now a few things cancel out. if you look at this thing, this cancels and the whole thing gives us a +1. This gives us a +1 while this gives us a -1. So this and this cancel out and we are left with only the two second terms that are going to be ln of n minus m minus ln of m is equal to ln of
Are you writing on your
yeah,
thing?
sorry, the Wi-Fi, this is, sorry about that.
Also, I had a question in the Stirling's formula. I'm guessing that there is a factor, another, I think there's this n minus m that separately comes off, and are you ignoring that for some reason?
Yeah, let me get to that in a moment once this stupid Wi-Fi connects. Sorry. Yeah, so you're saying n ln n minus n, right?
Yeah, that minus n factor.
It's going to be negligible compared to the terms I have. Let me write it down once this connects.
Also, I think it cancels out because this plus m term comes from the third term.
Yeah.
Oh, that as well. Yeah, and then when you differentiate that, the n just goes off. Yeah.
Yeah.
Cool.
Great. Yeah, so here you would have had n minus m ln n minus m, which we did account for, minus ln n minus m, right? And then the second one, we would have had m ln m minus ln m. So this and this would cancel out, as Shams said. If this confuses you, Shams is the guy. Ask him on Slack and he will do it for you in detail, or I will do it for you. But that's the key expression we just derived, is that ln of omega. So I wrote a bunch of algebra here. All I did was to differentiate things carefully. I had ln omega is equal to ln n factorial minus n minus m, and differentiated it. I got ln omega is equal to ln of n by m minus 1. Let's call this as equation number 4. Okay. No, that's not ln omega. That's partial ln omega by partial m. So that is equal to, what is this equal to? We just did partial ln omega by partial m. So partial ln omega by partial m is equal to this. We don't have our beta yet. What's our beta? Beta is partial ln omega by partial e at constant n. What is E? E is m times epsilon at constant n. And epsilon here is a constant, right? So we can remove epsilon and we can write it as E is, beta is 1 over epsilon partial ln omega by partial m at constant n. So now we can use this thing in equation 5 from equation 4 and get our beta, right? So let's do that. So we have, just to rewrite the last equation for continuity, we have 1 over beta is equal to 1 over epsilon partial ln omega. Maybe I should write smaller letters and not like an elephant, by at constant n. And in equation 4, we just showed that partial ln omega by partial m is ln of n by m minus 1. So this is 1 over epsilon ln of n by m minus 1. And now we are getting somewhere. Now we have something interesting. So we have just shown what have we shown? We have shown that I'm a bit worried about, oh yeah, this is the mistake. This is beta, right? Beta is equal to 1 over epsilon. Yes. Otherwise, my dimensions were wrong. I was thinking, how do I have, you should never have, it's like it sent triggers in my head, because you should never have beta multiplied. You should always have beta multiplied by energy. Anytime you see beta divided by energy, be very careful, because beta multiplied by energy is dimensionless. Beta divided by energy has the dimensions of 1 over energy squared. So you better have a reason. And here on the right side, you have log of something, which is dimensionless. So clearly I had a dimensional mistake. So let's keep this to the right. So now we get something interesting. We get beta times epsilon is equal to ln of n by m minus 1. Okay? Or n by m minus 1 is equal to e to the power beta times epsilon. Okay? Or n by m is equal to 1 plus e to the power beta epsilon, or m by n is equal to 1 over 1 plus e to the power beta epsilon. And we suddenly have some very interesting looking expressions, which you will see again and again in StatMech, this 1 plus e to the power beta epsilon type of term. There is a reason why it happens when we do Bose-Einstein statistics and all, you'll see this happening. So this looks like just a bunch of algebra, but it's actually quite interesting, because remember what was m? If you go back here, m was the m is equal to number of particles in excited state, right? And we just calculated an expression for the fraction of particles in excited state. We showed that the fraction of particles in excited state goes as 1 over 1 plus e to the power beta epsilon. So this is an important equation. Let's give it a name. Let's call it equation number 6. Now we can calculate our energy. That's going to be E is equal to m times epsilon is equal to n epsilon by 1 plus e to the power beta epsilon, or I can also write it as n epsilon 1 plus e to the power beta epsilon to the power minus 1. Note that here I'm not using ensemble average symbol. I'm just calling it as E. Why did I do that? Why should I not have to use the ensemble average? I told you all in the first class that thermodynamics is, statistical mechanics is all about ensemble averages. Things make sense in an averaged way. Why should I not use average of E here?
Because for thermodynamic limit n tends to very high, and we can assume this as a microcanonical ensemble. And
that's always a good guess, but it's even simpler than that. Which ensemble are we looking at? Microcanonical. Right now we did it through microcanonical. So in microcanonical, the energy is fixed. We do not talk about fluctuations of energy. E itself is what we have. Its ensemble average is the same as in microcanonical ensemble. If you did want to write average E, it would be just dE E multiplied by some delta function, right? Whichever energy you force the system to be at. So in microcanonical, average of E is the same as the energy you imposed. When we go to our canonical ensemble case, then we will have to be careful. But for now, so this is just a note that we are looking at microcanonical ensemble. So now let's see if this expression agrees with the intuitive picture we wrote earlier. So equation 7, t tends to 0 or beta tends to infinity. As beta tends to infinity, this term will dominate. It will become infinity e to the power beta times epsilon, because remember, epsilon is positive. It is the higher state. If epsilon was negative, then your life would be in trouble. How would you solve the problem then? Well, you will have to shift your definition. You can think about that. So as beta tends to infinity, E tends to n epsilon by 1 plus infinity or tends to 0. So at 0 temperature, we do get that the energy of the system is 0. The system collapses into the ground state. As t tends to infinity, beta tends to 0, E tends to n epsilon by 1 plus e to the power 0 tends to n epsilon by 2. So we recovered the right limits that we had intuitively expected using the microcanonical ensemble approach. But on top of that, we recovered the intermediate behavior given here. And as an additional exercise, which will not lead to any points for you, but will give you intuition for later on, try plotting E as function of beta. Try to plot it and see how it looks like. Don't use Mathematica or Wolfram Alpha or anything like that. Try to develop intuition, it will help you. This function will show up again and again and again. So this is how we did our simple problem using microcanonical approach. The reason we could do it, the only physical idea here really was n choose m. It just boiled down to using n choose m, and after that doing some thermodynamic relations and getting things out of it. And you can solve a lot of problems using this way. Oftentimes, well, I can't say when this will be better than the canonical ensemble approach. Sometimes this is easier, sometimes it is not. You have to try it out and see how things go.
I have a quick question regarding using the microcanonical example here.
Mm-hmm.
So here we are discussing the 2-level system, which is relatively easier, but what about like 3-level systems or 4-level systems? I can see there's some complications in getting the combinatorial factors.
Oh yeah, your life will be terrible.
Yeah, is there any like tricks in using microcanonical example?
No, don't do it. Unless you are a master of number theory, don't do it.
Okay.
So you're absolutely correct. So what Jingchen just said is that this was a system with 0 and epsilon. But what if you had something which is 0, epsilon 1, epsilon 2, epsilon 3, and if you have done enough permutation combination, it boils down to some complicated linear equations where you have to think about how to partition numbers. It becomes complicated. It can be done, depends on how good are you with your permutations and combination. It can be done, but it is hard. And you will see that in some of the homeworks, I will give you bonus points for doing a problem using microcanonical ensemble and seeing if you can get it right. And you will see how it's hard. And so, yeah, but this is not always true. For certain problems, microcanonical is easier. For this problem, both are kind of easy. So the second approach we are going to take now is to tackle the same problem using canonical ensemble. And then I will ask you all as to which approach did you find easier. And I don't know, I think many of you will probably lean towards the canonical ensemble, but maybe not. Okay, so now we have to do canonical ensemble. Any more questions? Okay, good. So try to plot this and see how it looks like. It will help later. You can also try to get the heat capacity out of it and see how it looks like. Try to relate it with the Einstein and debye thing that we did. See if it makes sense. You can play around. Once you have this, that's why I said the only physics was in writing down omega. Once you have omega, it opens up a whole world. You can go and calculate whatever you want out of it, all sorts of thermodynamics. I just showed you average energy, but we could do way more. So let's think about canonical ensemble. Now, what's going to be our game plan? It will be kind of similar, but not exactly. Our game plan will now be to calculate Q as a function of NVT, okay? And once we have that, we are going to get the Helmholtz energy from this. And I once again want to remind you that the connection between statistical mechanics and thermodynamics is really boiled down in expressions such as this one. We saw it for the microcanonical, now we are seeing it for canonical. Deriving that this is actually true can be a bit complicated. We did it for the canonical ensemble last time, remember, and we had to think about the average energy and things like that. But even if you forget the derivation, you should still be able to say it if you remember that the state function in thermodynamics whose natural variables are NVT is the Helmholtz free energy or Helmholtz energy A. If you remember that, you can directly write it down. So the natural variables are really important. Cool. So in order to do this, we have to calculate Q. How will we calculate Q? Q is our canonical partition function. Now we have to go to every microstate nu and calculate the energy of that microstate E nu, exponentiate it, and take the sum, right? This is what we have to do. Now, what is this microstate? This microstate, I drew it here for you. This is a bunch of binary numbers defining which state your system is in. Is it in 0? Is it in the ground state? Is it in the excited state, right? And in each such microstate, you can write down the energy as E nu is equal to summation epsilon nj, where nj is equal to 0 or nj is equal to 1, right? Does this make sense? If particle number 1 is in ground state, then nj is equal to 0, and the energy you get that from that particle is equal to 0. If particle number 1 is in excited state, then nj is equal to 1 and epsilon nj is equal to epsilon. And this is how you sum it up, right? So this is our way of writing down the energy. Let's call this equation 8 and let's call this equation 9. Now, at first glance, the math is going to get funky. You would be like, oh no, that macrocanonical ensemble approach was way easier. But then some nice things will happen. We will use some nice properties of the exponential and it will just simplify like almost like magic. It's really nice. So let's use 9 in 8. What do we get? We get Q is equal to summation nu. And again, what is nu? Nu is summing over binary numbers of length n. It's a huge mega summation. So nu is really summing over n1, n2, n3, nn equal to 0 or 1, right? That's what nu is. We have a lot of these sums. How many sums do we have? How many such sums will we have? Any ideas? Two to the power n, right? Because every particle can exist in two states, 0 or 1, and all of them are independent. So you have 2 to the power n contributions to the summation. But on top of that, inside we have e to the power minus beta e nu. Let's write it down as exponential minus beta summation over nj is equal to 0 to 1 epsilon no, I did something wrong here. This is not nj. This is not summing over j. This is not summing over nj. This is summing over j, which goes from 1 to n. Sorry about that. So please pay attention. This is something I had written wrong. You have to go to every particle and think of its energy. It will either be 0 or epsilon, and it can be written in terms of these nj variables. Later, these nj variables will show up again, and we will call them occupation numbers. It does not really consider us at this point, but we will be visiting this concept later. For now, just make a note, it's called occupation number. So this summation is actually quite complicated. It goes from j equal to 1 to n epsilon nj. So that's a horrible summation, right? At this point, you must be thinking, or at least when I first saw it, I thought, well, that n choose m was great. I could just use Stirling's formula and get going. This is a summation with 2 to the power n terms, and each term itself is a summation of n terms with lots of variables floating around. But let's proceed with it carefully. What we are going to do next is to write down it. We will keep the outer summation the same as it is. It is n1, n2, and n is equal to 0 or 1. But now we will use a wonderful property of the exponential, which says that e to the power a plus b plus c is equal to e to the power a multiplied by e to the power b multiplied by e to the power c, right? Instead of exponential of summation, we can write it as product of exponentials. right? That's what we can do here. And then this thing becomes interesting. This summation that you had, it becomes product. And this is the first time I think we are using the product symbol in this class. So far we have used summations. We have a product which goes from j is equal to 1 to n. And we have e to the power minus beta epsilon nj. This transformation that we just did is super important. It's super important. It will show up again and again in StatMech. This simple idea that exponential of summation is the same as product of exponential, at least in classical StatMech, this is quite easy. If you're doing quantum mechanics, life can be complicated. Things don't commute with each other and you have to be very careful, but this is mostly classical StatMech. When we do quantum StatMech, we will use shortcuts to get our quantum in, but mostly this will show up many, many times. So pay attention. Let's go through it once again. What would you do over here? We are going to sum, Q is summation over microstates of e to the power minus beta e nu, right? That's my Q. What is nu? Nu is a set of binary numbers. N1, N2, N3, Nn, they can all be 0 or 1. And in top of that, I have to write e to the power minus beta e nu. What is e nu? For e nu, I use equation 9, which says that e nu is going to each particle, seeing whether it is in state 0. If it is in state 0, you give it nj equal to 0. If it is in state 1, you give it nj is equal to 1. That's our e nu. So we have this complicated expression, but now we notice that e to the power summation is equal to product of exponentials. So we have written it in a form which still looks ugly, but if you hold on for just a couple of minutes, you will see how it simplifies. Any questions about this? Okay, so let's spell out this summation over microstate explicitly. What does it mean? It means we go to N1. N1 can be 0 or 1. We go to N2. N2 can be 0 or 1. We go through N3. N3 can be 0 or 1. We go to N, capital N, which can be 0 or 1, right? That's how we got this to the power n number over here. And for each of them, we have product of j is equal to 1 to capital N e to the power minus beta epsilon nj. Now notice something interesting. This can be simplified. In fact, this equation is so important, I will write it again on the next page, and let me number my pages. 4, 5. Let's write down equation 10 again on next page. Equation 10 says that, what are we talking about? We are talking about Q. Equation 10, we just wrote down Q is equal to N1 equal to 0 to 1, N2 equal to 0 to 1, N capital N equal to 0 to 1, product of j is equal to 1 to capital N e to the power minus epsilon, beta epsilon nj. And now notice that this thing itself is e to the power minus beta epsilon n1, e to the power minus beta epsilon n2. This term can be brought over here. N1 is the only variable, N1 shows up only over there. This second term can be brought up over here. And we can simplify this summation now and write it in a really neat manner, which looks like N1 is equal to 0 to 1, e to the power minus beta epsilon n1, N2 is equal to 0 to 1, e to the power minus beta epsilon n2, and n is equal to 0 to 1, e to the power minus beta epsilon n. And that's really nice. Why is that really nice? Because this one is a trivial summation that we can do by hand. That is n1 is equal to 0, becomes 1. N1 is equal to 1, it becomes e to the power minus beta epsilon. And you know the amazing thing? All of them are the same. They are just variables that we have different, but when you sum it up, you just get 1 plus e to the power minus beta epsilon n times, or q is equal to 1 plus e to the power minus beta epsilon to the power n. And that's our equation 11. And now we are ready to have fun and get our thermodynamics out. Therefore, minus beta A is equal to ln Q is equal to n ln 1 plus e to the power minus beta epsilon. And we have the Helmholtz energy, right? We still need to think about the energy. We are interested in the average energy of the system, not the Helmholtz energy. We use our thermodynamic relation. E is equal to minus partial ln Q by partial beta. We derived this last time for the canonical ensemble. And now keep in mind is we should really be careful and use our ensemble averages, because in this second approach, we are allowing energy to fluctuate, right? So we have to talk about the average energy. So the average energy in this case can be obtained from differentiating equation 12 with respect to beta. It's a trivial differentiation. We have minus n. This whole thing gives us 1 plus e to the power minus beta epsilon. And then we differentiate e to the power minus beta epsilon multiplied by minus epsilon. Minus minus goes away. We get n epsilon e to the power minus beta epsilon by 1 plus e to the power minus beta epsilon is equal to n epsilon 1 plus e to the power beta epsilon to the power minus 1 as equation number 13. And if you compare it, it is exactly the same as equation 7. Same as equation 7. Both approaches gave us the same expression for the average energy. So once again, you can say it's the same expression. So if you want to calculate the average energy as beta tends to 0 or as beta tends to infinity, you will get the same answer as you got for the microcanonical. So this just shows you clear-cut as to how, through this example, that you got the same thermodynamics out of whichever ensemble you picked. The math was different. For microcanonical ensemble, it became it's counting everywhere. StatMech is essentially counting. However, for the microcanonical ensemble, it was two-state. We could directly use the combination formula. For canonical ensemble, we had to write down the Q, which seemed quite daunting. But then we used this nice property that e to the power summation is equal to product of exponential. And that really simplified things. So just like I think Jing Chen mentioned that the microcanonical approach will be in trouble if we did not have only two states, but we have 0, epsilon 1, epsilon 2, epsilon 3. When do you think this approach will fall into trouble? Can you see an example when we will have issue with this approach? Can anyone think? Or is this going to be wonderful? It will work all the time. You can be creative. So it's not obvious at first glance. The reason why we could do this approach worked is because this thing had a nice form, right? It was just e to the power minus beta epsilon nj. But now imagine if instead of just nj terms, you had product of nj's, nj multiplied by nj plus 1, nj plus 1 multiplied by nj plus 2, right? Then you won't be able to do this. You won't just have a product of different summations, different terms which were the same. If this term was more complicated, then our life would be in trouble. You might also think what would happen if instead of just 0 and 1, we had many states, then actually life won't be in trouble. And we will visit that in when we do quantum statistics, we will look at that. So this approach is quite powerful if the particles are independent. if the particles are dependent, then this type of factorization does not work out. In fact, I want to spend some time and think about equation 11, which I think is a really beautiful equation and shows you as to why did we go about calling Q as the partition function. Notice something nice happened in equation 11. Equation 11 says that n particle partition function is a product of n one particle partition functions, right? So let's imagine, let's take a step back and let's think about approach 3, which Chandler doesn't talk about, but we could be very smart about this problem. How? We would say, well, our n particles are independent, right? So let's just focus on one particle. If I focus on one particle and try to calculate its partition function, what would that be? That would be summation over microstate e to the power minus beta epsilon nu for that one particle. But for one particle, this is really trivial. The microstate can be nu with E equal to 0, nu with E equal to epsilon, e to the power minus beta epsilon nu. That would be 1 plus e to the power minus beta epsilon. And then you could say, since the particles are independent, therefore Qn is equal to Q1 to the power n is equal to 1 plus e to the power minus beta epsilon n. And you have equation 11. So this approach 3, you could have got an equation 11 in 2 lines. And that's a completely valid way of doing this problem. The reason this could work is due to this property. This is valid only for independent particles. Why do you think this is valid for independent particles? What's the idea here? Why did we write this? Why could I write this with confidence? Any ideas? What gave me the authority to write that equation? Apart from being the instructor for this class, what's the thermodynamic authority for writing that expression?
Helmholtz free energy is extensive.
Exactly. Helmholtz free energy is extensive. If you take 2 particles who are not talking to each other and add it up, if you double the system size, Helmholtz free energy should be extensive. And Helmholtz free energy is log of partition function. Therefore, partition functions should multiply with each other. But if you had the particles dependent, then this wouldn't be true. So for this problem, approach 3 is the preferred approach that you should take. However, always look at the problem, try to see how to set it up. And the homework 2 will give you lots of problems to think about it. The problem, you can do it whichever way you want. It's really up to you. And one of the things, yeah, so for independent particles, the partition function tells you that it's really, it's a product. It partitions into a product of things, and that's where the name comes from. And that approach 3, as you can see, clearly is way simpler than approach 2 and approach 1. But here you have to use this intuitive idea that Qn can be written as Q1 to the power n. If at the same time I told you that the particles are not independent, if I removed this approximation, then we are in deep, deep trouble. In fact, we are in tremendous trouble. I don't have an easy way to tell you how to solve the problem. Most of this semester, we will be doing independent particle systems. Now, you might say, what is independent? How is that anything to do with reality? But later, when we deal with dependent particles, we will say that the dependence between particles is kind of weak, so we can deal with it in a perturbative sense, or we will use mean field approaches to account for the dependence. That will lead to lots of nice ideas on how to build upon it. But this independent particle approach will always be our starting point. So for dependent particles, for dependent n particles, what do you expect? Should Qn be larger than Q1 to the power n, or should it be smaller than Q1 to the power n? What do you think? Can we say with confidence which way will it go? Can we? I don't know. I think that's an open question. I would like to think that it decreases because the things are dependent on each other. They reduce the number of ways, but I don't know. Maybe it can increase, maybe it can decrease. Something to think about. But it will be different. That we can say for sure. Okay, any questions about this? So this is all easy. It's not too hard, but it builds up, and that's the nature of StatMech. It's lots of simple concepts, simple manipulations that keep piling up on each other, and you always have to use thermodynamics as your best friend. If you want to do useful things with statistical mechanics, you can do fun things with statistical mechanics, but if you want to do useful things, you have to use these thermodynamic relations. And so that's why 684 is listed as a prerequisite for this class, because it really, really helps. Okay, if no more questions, let me wait for a moment. No one have any questions? How is that possible? Okay, I'm going to start Grand Canonical Ensemble, but what I want to do first is to hand you your homeworks. So I'm going to send you your homeworks on Slack. You will get it as direct messages, and open it, have a look at it, and then I'm going to walk through the answers one by one. I don't really want to start Grand Canonical Ensemble right now. It's a new topic. It's not very hard given what you have done, but it's a new topic. Let's do it next time. So, and I'm trying to recreate the classroom experience. So I'm just, so Z, I sent you your homework. This is an experiment. Maybe next time I will just send it to you beforehand, but it's a virtual environment. We are all allowed to experiment.
Okay, I see it.
Good. If you don't see it, let me know. Otherwise, the default is that you see it. I know Slack works. Eric?
Give me a sec while I open it up, see if I'm getting it.
Maybe this will be a disaster. In that case, I won't try this next time. Pierce? Yeah, so open it, have a look, and then I will walk through the answers carefully. Well, not carefully, somewhat carefully. For some of the questions, I want to discuss it. Michael? Normally, this is a nice thing to do in class because I get to see people's faces, but you know. It would have been nice if in Google Forms, I could have set up a system where the answer goes back to you, but I can't do that. Smithan? No, Smrithan. Even I got your pronunciation wrong this time. Smrithan.
You just like to see people's faces because of what points they get or something?
No, so I can see how you look like. You know?
Cool.
It's a graduate class. You shouldn't worry too much about this, but hopefully, yeah, this is a slow process. Next time, I'm just going to send it to you in advance. Nicholas Fisher. Do you prefer Nicholas or Nick?
Just Nick usually.
Right. And you are in chemistry, right, Nick?
Sorry, say that again.
Are you in chemistry or chemical physics? Which one are you?
Chemistry.
Chemistry. So Slack is already protesting. Did it it work? Because this is the free Slack, so it thinks, oh, no, it's working. Okay, we got Nick.
Yep, I got it.
Cool. Oh, okay, next time I'm definitely emailing it to you in advance. This is too slow. Neha. Neha, which program are you in?
Computational biology.
Computational biology. I think this is the first time I have a student from computational biology. And you did take 684, right?
Yeah.
Okay. How was that?
Yeah, I could do better.
Was it fun?
It was funnish.
Funish.
I mean, I need to work on it.
That's okay. You come from a different background. So, some of these classes are often biased towards students who have taken them in the past. And of course, so I'll stop screen share now. There is nothing to share. Yeah, this is a slow process. So thank you for bearing with my experiment. Next time, I'm just going to send it to you in advance. It would have been way faster. Faye. Also, there are a lot of you. There are like 18 of you. Grishma. Okay, I hope that we will. Okay, we have only 5 left, so that's great. Emma. Emma, you are in class today.
Yes, I am. Mhm.
I thought you had a group meeting this time.
Oh, yeah, I do have a group meeting, but I work something out with my advisor.
You are not double zooming, right?
Beg your pardon? Am I double zooming?
Yeah. Do you know double zooming when you attend 2 Zooms at the same time?
No, what does that mean? You mean like I'm listening to 2 things at once?
Yeah.
Sorry, you keep breaking up. I don't know what's wrong with my internet connection.
Don't worry about it.
No,
Okay.
I'm not double zooming.
Okay, Jing Chen, we are almost done. Meenal. Yeah, okay, definitely not doing this next time. Mention. Last semester, I had a 100 student class. So of course I couldn't do this there. So there I was using Gradescope, so it would get released directly. But I don't like the grading system in Gradescope. It's kind of hard for me to leave comments on your homeworks, which I have been able to do here directly on my iPad. And so there are pros and cons of everything. Okay, we have only 2 left.
Which class had 100 people in it that you taught?
PCAM 481.
41 had 100 people in it?
Yeah.
See, this seems wild. No,
Oh, it's so much fun. Teaching thermodynamics to undergrads Monday, Wednesday, Friday at 9 a.m. It's quite an experience.
yeah, I have a funny thing. Since I did chemical engineering, I didn't take PChem, I didn't take 481 as my thermo because I had engineering thermo, but I
Oh,
took,
you took it with Jeff
all the other
Clara, is it?
yeah,
I am sure he teaches a very good class.
yeah, it was a lot of engineering. Chemical engineering has a lot of charts. So that was one of the things that certainly feels unique to it.
Okay, so now everyone has received their homeworks, and what I'm going to do is to walk through the answers. So, and sorry for the delay on this. I don't want to waste your time. Next time I will give you these in advance, and I will just walk through the answers. So hopefully you have a copy of your answer sheet open. The first problem, let me do a screen share. So our visiting student can also see the problems. We don't want to have the visiting student feel left out. Okay, great. So let's go to this. Okay, the first problem, the first part was flipping a coin 3 times and calculating what is the probability of getting 3 tails and at least 2 tails. You did it in different ways. Some of you explicitly counted the 8 possible combinations and counted how many things will it happen. So the correct answer is at least the probability of getting 3 tails is 1/8, and the probability of getting at least 2 tails is 1/2. I did not care about which way did you do it. I've given you points. The second problem was a probability density. You had to calculate mean, median, variance, and kurtosis. Most of you got mean and median correct. Some of you got variance also correct. Most of you got the kurtosis wrong, which just shows that higher moments are hard to calculate. I have not deducted any points for the kurtosis as long as I saw that you related that it captures something about deviation of the 4th moment, then I gave you points. Third problem is a Fermi problem. Many of you went into some of you looked up information from the internet, looked up the diamond back from 2 years ago, all sorts of creative solutions. I've given full points to everyone. Fermi problems are wonderful. There is a UMD physics website which talks about lots of Fermi problems. The idea is to get you thinking to back of the envelope calculation. There is no right answer here, really. One such Fermi problem is estimate the number of piano tuners in Chicago. And I think even the International Physics Olympiad once in a while has a Fermi problem. And there maybe they are more picky than I was. Fourth problem is very important. In fourth problem, which comes from Macquarie, you're given the expressions for the heat capacity for an Einstein model and for a Debye model. And you have to calculate the temperature dependence. Almost all of you got the right high temperature dependence, which is 3nk, 3 multiplied by n multiplied by Boltzmann constant. Very few of you were careful enough to get the low temperature limit right. You rushed and you wrote both of them go to 0, which is correct, but that's not what the question asked for. The question asked for expressions. And in maybe 4 lectures, we will be revisiting this and spending a lot of time on this. Chandler, in true Chandler style, gives the whole problem as a homework problem, but we are going to take time to go through it because I love this problem. And you will see that Einstein's problem gets the heat capacity going to 0 as exponential, which is not true. In the Einstein model, you will see that Einstein was a bit lazy the way he set up the problem. He was not lazy in general, no doubt about it, but for this problem he was. So his heat capacity dies down very quickly. Debye was able to come up with an approximation and it dies down slower. So T-cube dependence is famous for Debye, and that's what I wanted to see. So if you just went to 0, 0 for both, I deducted 2 points, which I think is not too unfair. The fifth problem, most of you got right. It's a classic thermo problem. It's the perfect relation between Cp and Cv. If you want to do more on this, you can put in the relation for an ideal gas and see it comes out to NR, something proportional to the gas constant. And it's also important to keep in mind here that Cp is always higher than Cv. We discussed this in class as to what's the physical reason for this. Problem 6 uses Clausius-Clapeyron equation. If you use Clausius-Clapeyron equation, which uses the enthalpy of vaporization, it's quite an easy problem to solve. The temperature turns out to be 402 Kelvin. This is a problem I actually gave in my PChem 481 class in the final exam. That's where I gave it. So the 7th problem is, I think it's from an old chemical physics qualifying exam, or I don't know where, or maybe I made it. I don't remember. The 6th problem I definitely made. The 7th one, I think I took from a previous exam and modified it in different ways. So it's an adiabatic process. So you have to remember that Q is equal to 0. So you can talk about change in entropy. And the first part is just a bit of algebra, given that. The second part is also a bit of algebra. If someone is confused about problem 7, I will be happy to release a model solution to problem 7 that you can go through it. The key point in problem 7 that I want to mention is that in part C, the answer that you get is very close to 300 Kelvin. It is around 302 Kelvin or 308 Kelvin, something like that. And if you calculate the fractional change using that much temperature, it turns out to be a very small fractional change. Hence, it is a valid assumption. Many of you got very funky temperatures in 7C. I have seen negative temperatures. I have seen million degrees Celsius. Try to see why that happened. Think through it once again. The answer should be around 308. Think about it, and I'm happy to post a solution to this. Apart from that, the homework 2 is now out. It's a bit harder than homework 1. I will be having office hours on Thursday. I will be happy to give you some suggestions there if you're stuck on any problem. And it's due in a week. And we will meet Thursday morning where we will talk about grand canonical ensemble. I'm going to hang out for a couple more minutes if you have any questions. Otherwise, the class is over.
Can you hear me?
Yeah.
Yeah. So on Thursday, what time?
Your audio lost.
Oh, what time on Thursday you have the office hours?
It's written in the syllabus. You check that
Like-
before I tell you a wrong number.
Yeah, no, like, should I mail you about like for a Zoom link or?
Have you seen the syllabus? It's all mentioned there. It's the same link as the class and the time is mentioned in the syllabus, okay?
Oh,
So please check that because if I tell you something now.
yeah, just yeah, it says Thursday or by. Yeah, great. So the thing is, I have a TSC and I have questions for
Your audio is really bad. Can you?
Yeah. So so that time I have a TSC, and so so if I have question, I think I will just.
Yeah, you can send me a direct message on Slack. If you cannot make the office hours, if we cannot resolve it on Slack, we can find some other time because office hours are always tricky to find for everyone.
Yeah, thank you.
But yeah, any other questions? Okay, so this class was not too hard, but we did a couple of concepts which will show up again and again, especially the canonical ensemble approach to solving the problem. It had these manipulations which are quite common in StatMech. Look at it carefully and it should seem obvious to you. Otherwise, see you on Thursday. Bye-bye.